In this last section of chapter 1, we're going to focus on understanding the difference between the average rate of change and the instantaneous rate of change. Now, before we get into that lesson, I want to step back and look at the big picture so that you can understand the path that we've taken to get here, and seeing how these topics are related will really help your understanding. Let's think for a second about calculus in general. So calculus is made up of two major ideas. We have derivatives and we have integrals. And both of these topics are based on the concept of limits. That is how they were defined. That is why the first calculus topic that we looked at was limits, because everything in calculus is based on the limit. So obviously we have to learn that first. We also looked at the idea of continuity, because so many theorems in calculus are based on the assumption that the functions that we're working with are continuous. So that was an important topic too. So that was another reason why we looked at that in chapter 1. So now that we are past the main idea that everything is founded on, the concept of a limit, and we understand continuity, which a lot of the theorems are based on, we're working our way towards the first major branch of calculus, which is called the derivative. Understanding the difference between the average and instantaneous rate of change, and then also how to calculate the instantaneous rate of change, is going to be the last step we take before actually defining the derivative. So this is what we're building up to. So let's first look at graphically the difference between the average and the instantaneous rate of change. We have this function here in blue, and then we have two lines. We have a black line and a red line. Notice that this black line passes through the function at 2 points. This black line right here, this point here and this point here is where it passes through. When we have a line that passes through 2 points on a function, that line is called the secant line. And the secant line gives us the average rate of change, because we're looking at the rate of change between 2 points. So from this point to this point. So the slope of that line is going to be the average rate of change. On average, what happened from this point to this point? In between, it changes. So that's why we're calling it the average rate of change. And that's why we need 2 points. And again, just to remind you, when a line passes through 2 points on the function, that's called a secant line. Then to calculate the average rate of change, you would use the difference quotient, which is just a fancy way of finding the slope, but we're doing it more generically. Now the red line here, notice it only touches the graph in 1 point. It doesn't pass through 2 points, it touches just at that 1 point right there. So this is called the tangent line. Now, because it only touches the function at that 1 point, then what we would call that is the instantaneous rate of change. It's not the rate of change between 2 points. It's specifically at that 1 point. And that's what we call the instantaneous rate of change. It's the slope of the tangent line. And then what we're going to do is, to calculate the instantaneous rate of change, we're going to use the difference quotient along with limits to calculate the change in just that 1 point, and we'll get to that soon later in the section. We're going to look at the average rate of change first. This should be just review, but since it's important and we're focused on it in this section, let's do a quick review. So the average rate of change of a function is when you take the change in the dependent quantity, which is your y, over the change in the independent quantity, which is your x. So we take y2 minus y1, and then x2 minus x1. When we look at it in terms of function notation, we have f of x2 minus f of x1 divided by x2 minus x1. So here's our picture of our generic points, x1, y1, and x2, y2. And this is going to be a secant line because it's passing through 2 points on the function. And so our average rate of change is going to be the slope of that secant line. In example 1, it says for the function f of x is equal to 3 times the square root of 2x plus 1, find the average rate of change with respect to x over the interval from 2 to 8. This is not a point like x, y. Sometimes people forget. When you have brackets like that, we're talking about the difference or an interval of the x value. So this is saying we're going from x is equal to 2 up to x is equal to 8. So to find the average rate of change, we need, using this formula, to find the value of the function at 8 minus the value of the function at 2. That's the change in y, and then we're dividing by the change of x, which is x minus 2. When we work out all of that arithmetic using order of operations, we're going to get that the average rate of change is 1. This means that the secant line that passes through x is equal to 2 and x is equal to 8 on this function has a slope of 1. Let's look at the next example. It says a college bookstore sells mechanical pencils for which it pays $1 each. The manager of the bookstore feels that if selling the price is X dollars each, she will sell 12 minus X pencils each week. The bookstore has a fixed cost of $10. The function relating to the profit, P is the name of the profit function, and the selling price is X. So here's our profit function. So since the selling price is X, the way that I would read this is I would plug in the selling price and it would give me the profit that I would make at that price. And we want to limit the domain because we're only talking about doing this over the interval from 2 to 11. So we want the prices to stay between 2 and 11 or equal to 2 and 11. It says find the average rate of change of the profit with respect to the selling price. And we're looking at the change of selling price from $3 to $6. So what we need to do is find the corresponding profit values for $3 and $6. So that's our P of 6 and our P of 3. We're going to subtract that. So that's the difference in the profit from 3 to 6. Then we're going to look at the difference in the price. That's our X. So we're going to take 6 minus 3. And when we work that out, we are going to get an average rate of change of 4. Now, when we interpret this, because it's in the context of a problem, we need to identify the independent and dependent variables. Because remember, the top value when we're calculating the average rate of change is the dependent, or what we look at is the output or the y value. And then below is the x or the independent value. Since our slope is 4, we would say every time we increase the price by $1, we would get a profit change of $4. Average rate of change works only for between 3 and 6 because that's how we calculated it. If we picked a different 2 points, then we would get a different average rate of change. Now, we're going to look at average rate of change in a different format. It's going to be the same thing, the same meaning of what we're doing, but we're going to look at it in a different format. And that way we're still leading up to the definition of a derivative. We're working our way up. So when we think about the difference quotient, we take the change in y over the change in x. And when we use function notation, we're taking f of x2 minus f of x1 over x2 minus x1. But now, if we look at the picture in a little bit of a different way, if this is our first x, and this is our second x. Rather than calling it x1 and x2, what we're going to do is look at the distance between the two x values. We're going to call that h. So if I'm sitting here at the first x and I add a distance of h, then my next independent value is going to be x plus h, because I take x and I add that distance of h. So instead of calling it x1 and x2, we're going to call it x and x plus h. Which means when we look at the corresponding y values, I would plug an x into the function to get my corresponding y value. So I would have one point that's x, comma, f of x. When I plug in x plus h as my second x value, I would have the ordered pair x plus h, comma, and then I would have f of x plus h, because I'm putting that x plus h value into the function to get the value of the function. So now we have the same meaning. We're still finding the slope, the change in y over the change in x. We're just looking at it in a different way. So when I take the difference in my y's, or my outputs, I'm going to take this y value, or this output, and subtract f of x. So I have f of x plus h minus f of x. In the denominator, I'm writing my changes in x. So my change in x is, I'm going to take this value for x, x plus h, and subtract x. When I do that, the x's drop out because I have an x and a minus x, and I'm left with just h, which makes sense because remember, on top we have the difference in the y's, and then down below is the difference in the x's, and the difference between the x2 and the x1 is h. So now we're looking at the difference quotient in a different way. It's still the same as f of x2 minus f of x1 all over x2 minus x1. It's the same thing, it's just in a different format. Just like 1/2 is the same value as 0.5, we're just looking at it in a different format. So now let's use this new format and find the difference quotient. Let's see, where's our function? Here's our function. It says our function is f of x is equal to 5x plus 8. And we're going to find the average rate of change using this form of the difference quotient. So to find f of x plus h, everywhere in the function, I'm going to replace x with x plus h. So in here, for this x next to the 5, I'm going to put in x plus h. So my function for f of x plus h, I would rewrite it as 5 times x plus h. This was the old x. We're replacing it with x plus h. Then we have this plus 8 here. So that's this function right here. Now we're subtracting f of x. F of x is just 5x plus 8. So I'm going to subtract 5x plus 8. This is very important. When you're subtracting the entire function, it's a really good idea to put parentheses around it so that you remember to distribute the minus. This minus here means you're subtracting every term in that function. So when we distribute that negative, this becomes a negative 5x and a minus 8. And when we start combining like terms, we get 5x and a minus 5x, so that drops out. Then we have a plus 8 and a minus 8, so the 8's drop out. And so I'm just left with 5h over h. So I'm left with 5h over h. I can cross off the h's. And then what I'm left with is 5. And this is exactly what we should have expected to get right from the beginning, because if you notice, this is a linear function. And linear functions have a constant rate of change, which is the slope. So that's 5. So we verified that we did this correctly by recognizing that this is a linear function and we should have had 5 for our average rate of change, no matter what 2 points I pick. So for every 1 unit of change in the x, we're going to get an increase of 5 in our output, or our dependent variable. So looking at example 4, we're going to do the same thing we did as the previous example, but it's going to get a little bit more messy because we're evaluating it with a quadratic. It's not hard, it's just going to get a little bit lengthy and we just have to be careful. So we want to find the difference quotient using this form right here, and we want to find the difference quotient using this function right here. So everywhere we see x in our function, we need to replace it with x plus h. We're evaluating f at x plus h. So when I plug in x plus h here and here, this is what we're going to get. We have a negative on the outside, and then I'm taking x plus h and putting it in for this x here and squaring it, plus 13 times, and then this x here gets replaced with x plus h, and then I just have this minus 22, the constant that I'm bringing down. Then I need to subtract f of x. So I'm going to subtract this entire function, not just one term. I've got to remember to distribute to all the terms. I want to distribute this negative to everything. So I'm subtracting negative x squared plus 13x minus 22. When I distribute this negative, and I'm going to square the x plus h, that's going to give me this down here. I haven't distributed this negative yet here. I did x plus h times x plus h. So this is what we get. I'm just going to bring that negative down. Here I'm distributing the 13, so I have 13x plus 13h, and then here I'm distributing the negative. So now everything inside here, the sign gets swapped. So that makes this a positive x squared, a negative 13x, and a positive 22. The next step is we're going to distribute this negative. So that's going to change all the signs on the inside here. They're all positive. It's going to switch to all negative. So from here to here, I have negative x squared minus 2hx minus h squared. And just everything else just gets dropped down. When I start combining like terms, now that I have everything expanded and distributed, a lot of stuff starts to drop out. So one thing that I see right away that drops out is this negative 22 and this positive 22. Another thing that I see drops out is the x squared with this negative x squared. Let's see, and then I have this positive 13x and this negative 13x drops out. What is left is the negative 2hx minus h squared plus 13h. And I haven't said this before, but I'm sure that you understood this. We have to remember to keep bringing down that h as well in the denominator. Now I have to try to simplify this as much as possible. If I notice on the top, everything on the top has an h. So we can factor out an h, and what's left over is negative 2x minus h plus 13. So this h here will divide out with this h here. I have h over h, which is 1, and it disappears. So now I'm left with just the negative 2x minus h plus 13. So this is my average rate of change between any two values of x. This is generically. So we found the generic average rate of change. So I can plug in any x and any h I want, and I will find the average rate of change for those 2 points. So for example, if x was 1 and the second x value over here was 3, I would know my distance between x and 3 is 2. So it would have x is 1 and h would be 2. So that's what I would plug in here, and it would give me my average rate of change. So by setting it up generically, we can evaluate the average rate of change at any 2 points we want on this function f of x. So now we're going to get into the instantaneous rate of change. So up to this point in this lesson, we've talked about the average rate of change, and we showed how there are two different formats that we can write the difference quotient. So when we rewrite the difference quotient with an h in the denominator, and then we slap a limit in front of it and we say we're going to take the limit as h goes to 0, that is going to help us transition from the concept of the average rate of change to the concept of the instantaneous rate of change. And knowing how to do this is going to provide a really powerful tool that you can keep in your tool belt with all the other things that you're learning. And this will help us investigate and analyze functions at a specific point. So to help you visualize this definition of the instantaneous rate of change, I have a link here to GeoGebra that shows how the secant line and the tangent line are related by taking the limit as h goes to 0, and it will show how as the limit of h approaches 0, how we get that instantaneous rate of change. So here is our GeoGebra example that's going to help us visualize how as the limit of h goes to 0, how it helps us define the instantaneous rate of change. So in this example, we have a cubic that's colored black here. And then we have our green secant line. And I know that the secant line is this green one because it passes through 2 points on the curve. Then I have the tangent line that's in this pinkish purple color. And I know that that's the tangent line because it only passes through 1 point on the curve. So if we look at our 2 points, so we have an x1 and an x2, but because we're going to use the format of the difference quotient that has the h in it, we're going to label our x1 and x2 as a and a plus h. So right now, a is sitting at 1.5, and a plus h, our second x point, is sitting at 2.5, which means the distance between them is 1. So right now, h is 1. Now, if we take the limit as h goes to 0, that's going to help us define the instantaneous rate of change. So I'm going to use this slider right here for x equals 1. Right now, it's at a distance between the 2 points is 1, but I'm going to close that distance in and make it smaller and smaller by using this slider. Now look at the value of h. As I slide the value of h, I'm taking the limit as h goes to 0 because you notice my h is getting smaller and smaller, and this distance between these 2 points, which is h, is getting smaller and smaller and smaller. So as I slide the second x point closer and closer to where those 2 points are pretty much sitting right on top of each other, that is when the secant line becomes the tangent line, because we closed in that distance between the 2 x values by taking the distance between them and closing them, which is the limit as h approaches 0. H is the distance between them. So that is visually what we're looking at here. When we get that secant line close enough to the tangent line, we can say that we have the instantaneous rate of change. So the slope of this line is the rate of change at just that one specific point. So now that we understand that if we use the form of the difference quotient that has the h in the denominator, and we take the limit as h goes to 0, which is telling us that we're closing that distance between the 2 x values, it's going to give us the instantaneous rate of change. So we are going to use this function here, the quadratic 3x squared plus 7x minus 2, and we are going to find the instantaneous rate of change at x equals 1, x equals 2, and x equals -4. So we first have to set up our difference quotient. We need to find f of x plus h. F of x plus h is what I get when I take x plus h and put it everywhere I see x in this quadratic. So I'm going to have 3 times this x here is going to be replaced by x plus h, and then we're going to square that quantity. Then I have to put x plus h in here to multiply it by the 7. So I have 7 times x plus h. Then I'm going to bring down this minus 2. So this right here is our f of x plus h. Now I have to subtract my function. So I just have to carry that down. Just remember, when you subtract the function, you have to subtract each term. So either subtract it and change the signs right away when you write it down, or put your function in parentheses to remind you to distribute that minus. Once we distribute the x plus h twice and we multiply that out and expand it, and we're going to distribute the 7 and distribute the minus, and we're just going to combine all like terms. Once we expand everything and combine like terms, things are going to start dropping out. If they don't start dropping out, most likely you forgot to distribute this negative here. Most of the time, that is where students make their mistake. So if you see things are not dropping out as they should be, go back and check to see if you distributed that minus. Here we have everything expanded and distributed. I have 3x squared with a minus 3x squared. I have a negative 7x and a positive 7x. What else? I have a minus 2 and a plus 2. What we have left is 6hx plus 3h squared plus 7h all over h. We can't take the limit yet as x approaches 0 because that would leave us with a 0 in the denominator. We still have to do some algebraic manipulations to get that h out of there. So we can factor and pull out an h from all of those terms, and then we can divide it out with that h in the denominator. And so now what we're left with is the limit as h approaches 0 of 6x plus 3h plus 7. So when we take the limit as h goes to 0, that's when we're going to make those two x values get closer and closer to where the distance is pretty much 0. So when we look and we use direct substitution to find the limit, I have 3 times 0. This is going to disappear. This 6x and this 7 does not have anything to do with h. So we just carry that down. The only thing that drops out here is the 3h. So what we're left with is 6x plus 7. This is our instantaneous rate of change. And now what we can do is we can find the instantaneous rate of change of any place on that quadratic by plugging in the x value at that point that we want to find the instantaneous rate of change. So if I want to find the instantaneous change at x equals 1, I would plug in 1 here for x and I would get 13. If I want to find the instantaneous rate of change at 2, I would plug 2 in here and I would get 19. If I want to find the instantaneous rate of change at x is equal to -4, then I would plug in -4 here and I would get out -17. Now remember that the instantaneous rate of change is the slope of the tangent line that touches just at that one point that you're looking at. So in these first two, in A and B, these are the slopes of the tangent line at x equals 1 and x equals 2. So these are positive slopes that tell me at that point my tangent line is going to be going up left to right. That also tells me that I am on a part of the curve that is increasing. When I look at x is equal to -4, that has a negative slope of the tangent line. So what that tells me is x equals -4, that point is going to lie on an interval in which the function is decreasing. We found the instantaneous rate of change. We understand what that means now. It's the limit as h approaches 0, so we're closing in those two x values really, really close. So now that we know how to define the instantaneous rate of change, we also know that that is the slope of the tangent line. So the slope of the tangent line and the instantaneous rate of change are equivalent. So let's look at example 6. A magazine publisher has determined that the cost C in dollars associated with X number of half-page articles is given by this function. So we have the cost is equal to minus 5x squared plus 200x. And remember, x is the number of half-page articles. And we are going to look at this only on the interval from 0 to 20 inclusive. So the first part says, if the magazine is currently running 12 half-page articles, what is the expected increase in cost if we were to run 13? And then we have a similar question down here. Part B says, if the magazine is currently running 15 half-page articles, what is the expected increase in cost if we were to run 16 of them? So we first need to determine the instantaneous rate of change. So we are going to find that by taking the limit as x approaches 0 of f of x plus h minus f of x all over h. When we find f of x plus h, that means we're taking x plus h and plugging it into our cost function everywhere we see x. That's going to give us this right here. Then we need to subtract our function, which is minus 5x squared plus 200x, remembering to put the parentheses around there. Then we're going to clean that up, distribute, square. Once we start combining like terms, we're going to get negative 10hx minus 5h squared plus 200h. Every one of these terms has an h in it, so we can factor it out and cancel it with this h in the denominator. When we do that, that allows us to use direct substitution when we find the limit. So now when I plug in h is equal to 0 to use direct substitution, this minus 5h drops out, and I'm left with minus 10x plus 200. So this here is the instantaneous rate of change of any value of x on that cost function. So if we want to find the instantaneous rate of change at x equals 12, we plug in 12 for the x, and we are going to get 80. What that means, remember, this is a slope or a rate of change specifically at that point x equals 12. The numerator is the change in our dependent variable, which is the change in the cost. And the denominator is the change in our independent variable, which is the change in the number of half-page articles. So this tells me when the company produces 12 half-page articles, at that point, if we wanted to increase the number of half-page articles by 1, that would cost $80. Now, this is just an estimate because we're looking at it specifically at that instantaneous rate of change. If we want to find the exact difference between producing 12 and 13 half-page articles, we can just directly plug in 12 and 13 into that cost function and find the difference. So this is 75 to find the exact difference in cost. So doing the same thing for 15, if we want to find the instantaneous rate of change, we're going to plug 15. So we have negative 10 times 15 plus 200. When we work that out, we're going to get 50. So this means when the company is producing 15 half-page articles, we can estimate that the change in cost when we increase by one more article would be 50. Then if we want to find the exact value, we can plug in 15 and 16 for x into the function and subtract, and we can find the exact difference in cost. Now that we've gotten a couple examples under our belt on calculating the slope of the tangent line, which is the instantaneous rate of change, I am going to show you how you can actually find the tangent line on GeoGebra. We're going to use this example here, x squared plus x minus 1, and I'm going to find the tangent line at x equals 1. So here's our grid on GeoGebra. I have defined the function already. That's this black curve right here, x squared plus x minus 1. If we want to find the tangent line at a given point using GeoGebra, what you want to do is you want to define the point. In our case, we want to find the tangent line at x equals 1. So we need the corresponding y value, which in this case is also 1. This is easy to read off the graph. If you need to find the corresponding y value because you can't see it clearly from the graph, you can always just plug in x is equal to 1 into the function and evaluate it. So to define a point, I'm just going to put parentheses and I'm going to put 1, 1. That's our point. And see how it labels it here for us. It gave it the name A. So our point A is where we're trying to find that tangent line, so it touches just at that one point. Now that we have defined our function and the point, you're going to use the command tangent, and I believe it's case sensitive, so it would be a good idea to make sure that you use tangent with a capital T. Then when the menu pops up, you want to choose tangent. You want to put in your point and your function. So you want to use this tangent command right here. You want to put in the point, and we define the point as A. So I'm going to put in A, comma, and then I want to use this function here, which we defined as f of x. When I put that in, it shows me on the graph the tangent line. Let me switch it to a different color so it's easier to see the difference. Okay, so here's our tangent line in pink, and it just touches at that one point A. So we can visually see it on the graph, and then we can see what the line is right here. Now this line gives us the slope times x minus 2, and 2 is the y-intercept. So if we want to find the instant rate of change, not the line, but the instant rate of change, that is going to be 3 in this case because it's the slope of the tangent line. Let's try another one. I'm going to clear that out. Let's try, let's do x to the third plus 2x squared, and let's say I want to find the tangent line at, let's say, negative 1.5. So first I need to define the point, negative 1.5. This function that we're using right now is h, so I'm going to put in h of negative 1.5. And it evaluated it for me and shows me that point on the function. So this point here that we're now using is labeled as B. So if I want to find the tangent line on this cubic at that point B, I want to use the command tangent. I'm going to use this option right here, tangent point function. I want to find the tangent line at B of this function h. So I'm going to put in h of x, hit enter, and it's going to give me the tangent line at B. So now if I asked you to tell me what the instantaneous rate of change is on that function at negative 1.5, you would tell me 0.75. If I asked you for the tangent line itself, then you would give me the entire equation for the tangent line. But the rate of change is specifically that slope.